In this video, let's look at a few examples on the effect of zeros. On the right, we have two transfer functions. The first transfer function, it has no zeros. It has two distinct poles in the left half of the S-plane. -2 and -1. Second transfer function has a 0 at -1.1, 0, -1.1. It's easy to see the two transfer functions have the same DC gain. In other words, if we apply the same step signal, they have the same final values. The figure on the left shows the step response of the two transfer functions. This blue curve shows the step response of the first transfer function. We know the step response of the second transfer function will be the response of the first transfer function plus a scaled time derivative of the original transfer function. Sorry, the original step response. Since the time derivative of the first transfer function is always positive, so the step response of the second transfer function is the step response of the first transfer function plus some positive values. Here it shows the step response of the second transfer function. We know the rise time is the time for the system, the response to grow from 1%, from 10% to 90% of the steady state value. 10%, 90%. Rise time for the first transfer function rise time for the second transfer function. You see here from this example, the major effect of the zero is to reduce the rise time of the step response. Now let's see another example. We have a second order systems with 0 at minus z. This transfer function has a unity DC gain. Now let's determine the effect of the 0 locations on the unit step response when z takes the values from 1, 2, until 6. Let's calculate the step response. We know for unit step response, the Laplace transform is 1 over s. So the output will be the transfer function times 1 over s. Then we write the output as 2 parts. The first part is the step response of a transfer function without zeros. The second part is the scaled time derivative of the transfer function without zeros. If we apply the inverse Laplace transform, we get the time response for the first part. Then the second part will be the time derivative of the first time function divided by z. Then we have 0 here. The time derivative will be 0. Then we have minus 4 will be 12 exponential minus 4t. We have minus 6 will be minus 12 exponential minus 60. Then divide by z. Then the total response will be the response of y1t plus y2t. The total response is 1 plus 12 over z minus 3 exponential minus 40 is from the pole minus 4. Have 2 minus 12 over z times exponential minus 60 is from the pole minus 6. Here, it shows the step responses for different values of z. First, let's look at the interesting case when the zeros are the same with the poles. So in this case, when z is 4, then the 0 and the pole, they can be canceled. That means the mode minus 4 is absent from the output. Then the total response will be the response of a first order system. That will be the dashed line here. Similarly, when Z is 6, so the mode minus 6 is absent from the output. And the response is the first order system due to the pole zero cancellations. We know pole zero cancellation can only happen when the pole is in the left half of the S-plane. As we mentioned before, when the zero is small and close to the imaginary axis, it has a substantial influence on the original input, original response. So let's look at this bottom curve. This is the original transfer function without any zero. It is the step response of a second order system with two distinct poles. When zero is added, now we see it produces overshoot. We know for standard second order system with two poles in the left half of the S-plane, real poles, there will be no overshoot. But because of the zeros, the step responses produce overshoot. And overshoot is most pronounced for small value of zero. That is, Z is equal to 1. We see when Z is 5, even though there are no zero pole cancellations, its step response is within the step responses of two first order systems, because the zero is between 4 and 6. There's no overshoot. Now let's look at the effect of zeros on standard second order systems with complex poles. If we study the step response, we know the Laplace transform of unit step response is 1 over S. Then the output is 1 over S times HS. Same as before, let's write the output as two parts. The first part is step response of a standard second order systems. The second part is the scaled and time derivative of the original response. Let's denote the first part is y0s, and the second part as yds. Then we can parameterize the zero by using the parameter alpha here. Then we can calculate the zero by letting the numerator be zero. Then we can cancel 1 omega n. Then the zero will be minus alpha beta omega n. Then beta omega n is sigma, it's minus alpha sigma. We know when alpha is small, it has a substantial influence on step response of standard second order system. But when alpha is large, it has little effect on standard step response. If we denote the step response, the time function of step response of standard second order system by y0t, then we know the second part is 1 over alpha beta omega n, the time derivative of y0t. Then the total response will be y0t plus y dt. That's this term. Now, let's look at the step response of the standard second order system with zeros. Here, we normalize omega n by choosing omega n is 1. The left plot shows when date 0.5, the bottom curve shows the standard step response when there are no zeros. So when alpha is large, the zero will be far away from the imaginary axis. So it has little effect on the response. That's the case when alpha is 100, its response is very close to the step response without any zeros. But when alpha is small, it has a substantial influence on step response. Especially when alpha is 1, the 0 is close to the imaginary axis. Then the step response is greatly different from the original step response without any zeros. The same patterns can be seen when beta is 0.707. Here, we also normalize the omega n undamped natural frequency by choosing omega n is 1. We see the green curve is step response of a standard second order system without any zeros. So when the value of alpha is very large, let's say 100, its step response is very close to the step response without zeros. But when alpha is small, let's say 1, then it has a substantial influence on the response. Then we see from the two plots, the major effect of zeros is to increase overshoot and reduce rise time. So the overshoot, let me show you the overshoot. Here is the final value. This is the overshoot when alpha is 1. Overshoot when alpha is 2. And overshoot when alpha is 4. So this overshoot when alpha is 100. So it's same, it has the same overshoot with the 1 without any zeros. Let's see the rise time. Here it is the rise time of the original system. Here it is the rise time when alpha is 1.